auditorium, and I curate public programs. Thanks for coming out tonight. Who's here for the first time ever? I thought I saw a few new faces. I hope you come back. Before we get going, I want to thank a few folks who make our programming possible: the Scientific and Cultural Facilities District, the Stewart Family Foundation, the Friends of the Longmont Museum, our many museum donors, and of course, our museum members. Do we have any members with us? Hey, members, thank you. We simply can't do all that we do without you. And we actually do quite a bit, and we're about to do quite a bit more. We're expanding the museum. We're going to be going north, adding a new gallery, expanding our lobby, sprucing up our entrance. We're breaking ground early in 2025, that is. It's pretty exciting stuff. And I think we're around 92% of our goal. So if you have a few $100,000 that you wouldn't mind letting us borrow or just giving to us, that would be fantastic. You can talk to me after the event. I also want to thank our media sponsors, the mighty KGNU Community Radio out of Boulder, and our newest sponsors, KUNC and the Colorado Sound. This is part of our regular Thursday night programming. Every Thursday evening we offer a panel, a lecture, a film, a performance, a talk, all sorts of things. We keep it eclectic here. Tonight, we're glad to have back the National Center for Atmospheric Research's Explorer Series. And I believe this is the 6th or 7th year we've been doing this now, and it's been very popular, and I think it really rounds out our programming well. This evening, we have Christine Shields joining us. She's a project scientist in the Climate Change Research section at NSF NCAR, with expertise in simulating Earth's past, present, and future climate with Community Earth System Model, or CESM, as you may know it. She earned her Master's of Science in Meteorology from Pennsylvania State University in 1991 and has focused her research towards understanding Earth's hydrological cycle in the context of climate change, with particular emphasis on atmospheric rivers, monsoons, moisture transport, cyclones, and weather extremes. Christine's research spans much of Earth's history, ranging from millions of years ago to future climate states under global warming. She is involved in a community-driven effort to define the uncertainties surrounding the various definitions of atmospheric rivers, and is particularly interested in how this uncertainty shapes our understanding of atmospheric rivers in an increasingly warming world. Ladies and gentlemen, please welcome Christine Shields to the Longmont Museum.
Hello, everyone. I want to first off thank the organizers, the Longmont Museum and the NSF Explorer organizers, for giving me the opportunity to talk to you tonight about the atmospheric rivers. And so we're going to talk a lot about atmospheric rivers, and in particular, how they might change in a future climate. So the first thing we really need to do is define atmospheric rivers. So I think actually I'm going to give you an outline first. So we're going to answer a few questions. The first is, what are atmospheric rivers? The second is where do they occur? And then the third question, finally we'll get to what the title slide says, is what happens to atmospheric rivers in a warmer world? So hopefully by the end of the lecture, you'll be able to answer every single one of these questions. Okay, so let's start off. What are atmospheric rivers? And so people, often tell me, well, what is an atmospheric river? Well, I'll know it when I see it. Well, that's not really that helpful when you're trying to explain what an atmospheric river is, so I think pictures really are helpful here. And so what I've grabbed here from the Wikipedia page, believe it or not, this is something that's accessible to everyone, is a couple satellite pictures of atmospheric rivers. Here we go. So the atmospheric river piece is this long, meandering, cloud-banded structure that's sort of extending from North America, which is over here, to the Pacific, the Japan and East Asia over here. So it's really long. It's like thousands of miles long. They're hundreds of miles wide, and they carry a lot of water. And one of the primary ways that the Earth transports moisture from lower latitudes to higher latitudes. And so this is just a couple different iterations of the same atmospheric rivers a couple of days apart from the NASA Earth Observatory, which is where Wikipedia got those images. So let's see, there we go. So I'm going to show you a lot of these tonight. These are a different type of satellite picture. What we saw before was a satellite picture where you can see the clouds and the Earth on the continents and the Earth. Here I'm showing you a type of satellite that measures water vapor in the atmosphere, and it's color-coded. So the deeper reds over up here indicate there's more water, and then it dries out as you go into the purples. And so you can sort of just pick out by eye where the big moisture pieces are. And so the atmospheric river this happened just a few weeks ago at the end of September. And you see this atmospheric river that's just moving all of this moisture, and it's making landfall sort of in the Seattle, Vancouver area. And I believe this atmospheric river probably produced like 4 inches of rain in the Glacier Bay area a few weeks ago. The other thing for the keen observer, which actually doesn't have to do with atmospheric rivers, is I just wanted, because this is neat, I wanted to show you. Over here, you see how this spinning thing is happening right there? That's the beginnings of Hurricane Helene that actually moved into the Gulf later and then was a very big impact to the East US, just as a curiosity. So you can see like there are parts of atmospheric rivers that actually carry moisture which is actually very similar to hurricanes. Different types of storms, but lots of moisture. So that's the key there. So how much water do these things carry? So I wanted to ask a question of the audience. I don't know if anyone wants to play along, but atmospheric rivers are the largest freshwater river on Earth. And so we have rivers in the sky. These are essentially rivers in the sky. So if we think about a river on land, that's like the Amazon River in the South America or the Mississippis in the US. If you think of an atmospheric river in the sky, how much water that has compared to, say, like an Amazon River or Mississippi? Anyone want to hazard a guess? You don't have to, but more. Okay, what do you think? Like 10 times more, 2 times more? 7. Okay, so someone solved the answer to this question. So actually, it's double the Amazon River in terms of freshwater, and about 7 to 15 Mississippi rivers. So it's a lot of fresh water. And then what happens? And this cartoon schematic that I have here shows you the beginnings. That usually happens for the west coast of the U.S., the ARs. The moisture sort of starts down here close to, there we go, like the Hawaiian Islands, and these types of atmospheric rivers that actually come up through the Pacific and impact California are often called Pineapple Express, because pineapple is associated with Hawaii, and so that's how that nickname sort of happened. But they come along the Pacific River, and then the Pacific Ocean, and then they hit the west coast of the U.S., and then they hit those, the topography there and the mountains. And so what happens when you have a mountain barrier and a bunch of water rushing at it in the sky, it gets like, there's a barrier there, so it gets forced up. And as it gets forced up, that air and that vapor in the air condenses into clouds, and that clouds becomes precipitation, and then that precipitation rains out in massive amounts usually, along the coastal regions and the lying areas, and snow up in the mountain ranges. So that's sort of the mechanics of how they happen. So how do we measure atmospheric rivers? We tend to use this term called integrated vapor transport, and it's just sort of fancy word for combining water and wind in the atmosphere. So you'll see this acronym IVT a bunch of times in this presentation. I'm just talking about this combination of water and wind. So how do we measure it? Like what's happening on the ground now? There are groups out there that actually have field campaigns, that have observations. They fly airplanes into these things, similar to hurricane hunters, where they take the plane, they go into the eye of the hurricane, and they measure all this stuff. There's a group at a Scripps, the Center for Western Weather and Water Extremes, that does these sort of things, except they do it for atmospheric rivers. And this is where we get a lot of good measurements. For those of you who are interested, those little diamonds, the diamond is that over in the tracks over here is where the NOAA went, the NOAA G4 went, and then the squares are where the Air Force C-130 went. But you can see the dots in the tracks along where all the crisscrossing the atmospheric river. And I guess I should have explained that this oranges and yellows and reds, this is the outline of the atmospheric river for this particular recon mission. So this is one of the ways we actually get key observations on what is happening inside atmospheric rivers. Okay, so the other thing I wanted to sort of explain in terms of what an atmospheric river is, we're still sort of going over this what is an atmospheric river question, is what it sort of, like from the big scale, the big weather scale, what is it, what's happening there? And so they're often attached to low pressure systems, and I'm sure everyone here has seen TV news where you've seen maps of the US with fronts and lows and highs and all that sort of stuff. So what's happening is typically there's a low pressure system out in the Pacific someplace, and there might be a trailing front with it. And then this atmospheric river really is sort of, it moves along that frontal system. So you have this background low pressure system, and then you have the atmospheric river that sort of gets scooped up into that whole low pressure system. And this is sort of what looks like, from a cartoon standpoint, this is where the atmospheric river lives, is sort of along this cold front. And as I said, it's like thousands of miles long and hundreds of miles wide and maybe a mile deep in the atmosphere. And then I've sort of transposed what's going on over here to over here onto this satellite picture, which is maybe something that might be more visually intuitive to people, where here's the low, here's the front, and this piece right here, where I've sort of circled in green, this is what the atmospheric river is. Okay, so here's another one of these satellites that shows moisture in the atmosphere that's color-coded. And I wanted to show this for actually a couple different reasons. This particular atmospheric river, which is this piece, this one right here, it's the Pineapple Express one, and it's sort of hitting Northern California, or Northern Central California. This was a very significant atmospheric river event that caused Lake Oroville, the dam holding Lake Oroville together, to disintegrate. And this was, if anyone is from California may have heard this at some point, this happened back in 2015, but it was 2017, but it was a massive catastrophe. And so it really gives you an idea of what type of impact that these types of things have. So that was the first point, because I'm going to refer back to Lake Oroville, and we call it the Oroville Dam crisis a few times later on in this talk. But the second point of showing this image is to answer this question, what is pushing these ARs along? We've been talking a lot about moisture, but we haven't really talked about wind yet. But you can sort of see, just with the flow of the atmospheric rivers, these things are getting pushed along by the general flow. So this is where the wind piece comes in. So I like to call this going with the flow, the jet streams. And so this is just a general explanation of what jet streams are. And so you can see the globe there. And the rotation of the Earth is sort of labeled over up here, just to sort of give you an idea. And you have these jet streams that are moving narrow and fast around the Earth in the same direction as the wind, as the Earth rotates. And so the blue ones, this is called the polar jet, and it meanders around, and it lives both in the northern hemisphere and the southern hemisphere. And the red one is called the subtropical jet. So these two types of jets are really important for driving where atmospheric rivers go. Okay, so this is a real-world example. We're going to start over here in this, again, this color-coded water vapor satellite image here. You can see, let's see if I can get the pointer there. There we go. You can see the moisture sort of coming up from the tropics, and it looks like it's getting scooped in, and then eventually being pushed into the Pacific Northwest there. So if we look over here to this globe, and this, by the way, is a really cool tool. So if anyone here is like a weather geek and loves to play with weather tools, I would go to this website, And you can play around with different, variables and temperature, wind, and look at all sorts of different stuff of what's going on around the Earth real time. So I grabbed this image at the same time that this atmospheric river occurred to show you. We've got here's our polar jet, and here is a piece of the subtropical jet. And so the moisture is sort of getting churned around and up here, and then eventually gets caught up in this polar jet. And we can see that really well right here. So this is just like a nice example of two tools that anyone here can do. You can go to this website to grab some of these satellite images, and you can go to the EarthNet, and then you can explore on your own. So these are all things that are accessible to the public. Okay, so measuring the strength of an AR. This is another piece of what an atmospheric river is, and how we actually categorize it, I guess. So we do have categories similar to hurricane categories. And this category was developed by the group at Scripps that I talked about before, CW3E. And they came up with these 5 categories based on IVT, which remember is this combination of wind and water, and then the duration. So we have how intense it is by measuring the IVT, the wind and the water, and then how long that intensity actually occurs. And so it's the combination of these two things that will define how intense the atmospheric river is. So on the vertical axis here, you have just the intensity, and then the horizontal axis here, you have the duration. So for the longer it lasts, you don't quite need the most extreme intensity to still have a category 5 if it lasts a long time. And so, yeah.
Can you slow down your laser a bit? We're looking at a 40-foot screen, and I can't find your laser.
Thank you very much. I will try to do that. Okay. So can you see it here now? Okay, so the horizontal axis is here, and that's duration. And then the vertical axis is the intensity. And so how we define the categories is if it lasts longer, you don't need quite as neat as an intense of an atmospheric river because it's lasting longer. So that is how we define these categories. And so we categorize them as 1, 2, 3, 4, 5, where 5 is the most intense. And this is a way we try to measure them or categorize them when they actually happen. Okay, so I think now we can move on to where do atmospheric rivers occur? So this is our second question. So typically they happen in the mid-latitudes, and that's where we live right here in sort of these temperate latitudes. I've talked a lot about the western US, western North America right here. And then I'm also, another common place for atmospheric rivers is also Europe, and the European atmospheric rivers sort of start here around the Caribbean, and they cross the Atlantic, and then they end up somewhere around Europe or the Iberian Peninsula. And typically, these atmospheric rivers sort of occur on the west coast of these types of continents. So that's the 2 examples with Northern Hemisphere. So here's some examples for Southern Hemisphere, because they actually happen globally all around the world. One example is Western South America. So here's an example of an atmospheric river that's making an impact on the west coast of Chile. And here is an example for the South Africa one. This is not the same image as the type of satellite as we have for Western South America, but this is a different type of observations that's similar, and I hope, it looks the same, so hopefully it's intuitive for you all. And here's the atmospheric river that's crossing over the South Atlantic and then impacting the tip of South Africa. And then we also have atmospheric rivers in Australia and New Zealand. And this is the only thing I actually couldn't find a nifty example with one of the satellites, so I just grabbed a cloud band satellite picture, sort of similar to what we saw in the very first image, that shows an atmospheric river crossing over in the northern part of Australia. So some other places atmospheric rivers occurs that isn't necessarily, are not as common, they're not as typical, but they're still impactful, are places like the northeast US. So here, this looks like a little bit of a fire hose. There's an amazing amount of water that's going up from the Caribbean and then making landfall around Halifax in Canada. So this is, they don't necessarily happen as often on the East Coast, but they still do happen. Another region that is known for atmospheric rivers that is not really typically thought of is East Asia. So here we have Japan, and here we have Korea. And we can see sort of a bullseye over the Korean region. And this area has a very active atmospheric river research because it is very impactful. And it's a different season from, say, like the monsoon. And then the Middle East, even though this is actually quite rare because it's very dry there, here's an example of an atmospheric river that's crossing over Africa and making impact here on the Arabian Peninsula. Okay, so they also happen at the poles, and I wanted to take a moment to give you some really cool examples of atmospheric rivers happening at the different ends of the Earth. This is over Antarctica, and this image right here is showing you this heat wave that happened in the East Antarctic continent a couple years ago, and this was in the news. It actually led to a collapse of the ice shelf called the Conger Ice Shelf. It was temporarily collapsed, but it was still a major event. And it was, at the top of the East Antarctic ice sheet, which is normally extremely cold. It was actually close to freezing, which is not really unheard of for that region around the world. It was a very intense heat wave. And you can sort of see the atmospheric river signature, here we go, with it, right along here. So I have the examples of the satellites next to it, and I apologize, you have to sort of rotate it. I have, this is South America right here, and Australia up here, and over here Australia is down here. So I couldn't find these images that were, without turning that one upside down and having the text upside down, and we didn't want to do that. So anyway, if you sort of flip it in your head, you can see what it also looks like in the cloud bands. You can see this atmospheric river that's making landfall in the East Antarctic continent here. And this is a satellite water vapor imagery that was similar to the ones I've been showing you, except the color coding is a little different here. And those white lines are showing you what the winds are doing. So you can see that this is it's coming off of Australia, and it's crossing the Southern Ocean, and then it's really slamming this East Antarctic area where the ice shelf was, which led to its collapse. So it was a really major event there. And then also, a couple years ago, there was a Hurricane Fiona that transitioned into like an extratropical storm that actually further fell apart and then turned into an atmospheric river that impacted the tip of Greenland. And so you can sort of see the signature of the tropical cyclone, and then you can sort of see it fall apart, and then you see it hit the tip of Greenland there. Okay, so now we're going to start with our third question. Why are atmospheric rivers important for climate? All right, so this is another audience participation question. So we know that atmospheric rivers are necessary to move a lot of water, usually from the tropics into the mid-latitudes, and then it could go further into the poles. So I have this picture here where I have the tropics sort of grayed out, because we're not really considering the moisture in the tropics. I just want you to guess what the surface area of the atmospheric rivers are. So they're pretty narrow and they're filamentary. How much space are those atmospheric rivers actually taking? What do you think? Which one? 10%? 50%? 10%? 25? Okay, we got them all. Well, it's actually 10%. So, but I mean, this is a pretty impactful statistic because they only take up 10% of the area, but they actually move about 90% of the water. So they pack a punch. They're not that big, but they pack a really important punch, and so therefore they're extremely important for our climate because they're moving so much water around. Okay, so the other reason why they're important for climate is because these extreme events occur. Now, I talked about this a little bit before with the Oroville Dam, but extreme events are very impactful to all of our lives. And so this is this still image of this image of the atmospheric river that I've showed you previously. This picture here shows the moment that, or close to the moment that the Oroville Dam collapsed due to the amount of water that was coming out of the atmospheric river. About 13 inches of rain fell in the span of a few days. And this was on top of a December and a January, because this happened in February. The previous December and January also had a series of atmospheric rivers that each produced inches and inches of rain. So this was sort of like the last straw. So, one example, this is an extreme event that was pretty impactful, so good. There's actually lots of examples. I actually wanted to show you an extreme event example from Antarctic, because I think this is also really cool. We don't really think about them in Antarctic that much, but they are actually very, very impactful. So that I have a cartoon of Antarctica there, over here, and I have a little red dot over a glacier called Thwaites Glacier. And so I have a colleague that went there a couple years ago to measure, to take like an ice core, which is what you see right here, to measure what the impact of some atmospheric rivers were that occurred on Thwaites Glacier. And what you see is in those dark banded areas, like from here to here and here to here, these are the moments where the hours and days that the atmospheric river occurred. And so a huge amount of snow contributed to the ice sheet. And so right now, the snow is typically, the precipitation and ARs typically produce snow on Antarctica. But this is something that could potentially change as we move into the future. Okay, so last but not least in terms of importance for climate, ARs are drought busters. This is an extremely important part of what atmospheric rivers do for the globe, is they actually dump a whole bunch of rain, and they actually dump a bunch of rain, and typically in places that need rain, like I'm giving you an example here, of California. So here is an example of sort of like a before and after. So the image over here on the left shows you, this drought, California, Nevada drought, this was from the drought monitor index, which is something that is produced routinely all the time, and I actually have references I can give you for that later, but these types of drought maps are produced routinely, and you can see that much of the area is in a drought. This middle panel shows you the precipitation that happened over that winter season from October to March, and there was a lot of precipitation. And then if you take the same snapshot and measuring the drought after the atmospheric rivers, you see that much of California was lifted out of the drought, and this is almost primarily due to atmospheric rivers. California tends to get most of its precipitation in the winter with these types of phenomena. Okay, so let's take a look at a recent example. So what I showed you was actually quite a number of years ago. Here we're looking at the atmospheric rivers that happened last winter. And we think of things in the climate world in terms of water years. And so a water year actually goes from October to October, because you want to keep that winter season where most of the precipitation occurs sort of together as one season. So this is water year 2023. And that image over there on the left is showing you the atmospheric rivers that occurred over the span of a number of days between December and January. And then here, we take a look at these drought monitor index maps. And so the map on the left there with California shows you some deep, deep drought that's happening before the water year. And then after this season is done, the season, it goes from October to October, but by March or the end of March, typically most of the precipitation has fallen, and so it's a good measure of what the water year will be. You can see that it's been completely lifted out of the drought. So very important piece of the climate. So around now, I'm wondering, you guys are thinking, well, you've been talking a lot about California. What about Colorado? I mean, we live in Colorado, right? So I thought maybe I would, talk a little bit about how atmospheric rivers are important for Colorado climate. And it's sort of like a secondary sort of a thing. I thought this is a drought monitor index I pulled off the internet just a couple days ago that shows you that where we are in terms of drought for Colorado. But the main point of this is just to sort of try to show you why atmospheric rivers could be important for Colorado too. So does anyone want to hazard a guess? I put this map up here because it's a hint. Okay, so we have the floor. You guys don't, maybe it's a complicated answer. Okay, so you have the atmospheric river, right? Remember, it hits the mountains. The water gets, everything gets pushed up, cools, condenses, forms clouds, precipitation, and a lot of snow. So that's the hint. There's a lot of snow. So yeah, okay, snowpack, right? The Colorado River Basin actually gets a lot of atmospheric rivers. And so the snowpack is something that's really important for Colorado. And so atmospheric rivers tend to supply a lot of snow to the snowpack. They also sometimes can make it all the way over. Depends on how strong the atmospheric river is. But when they do make it over, it tends to be, not really, it's not going to be like a California atmospheric river where it's going to be inches and inches of rain. It'll be something a little more muted. But the main impact is really just that snowpack. Okay, so now we finally get to the last piece, the last question, which was the title of this talk. Well, what happens to atmospheric rivers in a warmer world? Okay, so the first thing to think about to realize is that we can't take observations for the future, right? Because, it's the future, right? We're not time travelers. So we have to use a different tool to try to estimate what's going to happen to the climate in the future. And so we use these things called Earth system models. And Earth system models is just sort of a fancy way of saying it's just a really complicated computer program. And so in this complicated computer program, we're solving a bunch of equations. And those equations that we're solving is helping us to understand what is going to happen with the climate. And so I have here this picture of a globe, and it has this funny mesh over it. Because when we digitize things to run our computer model, we sort of wrap this mesh around the globe. And those intersection points we can think of as like different latitudes and longitudes around the globe, right? So those intersections is where we call those grid points. And in each of these little grid points is where we actually calculate stuff. It's where we solve our equations. And so once we've solved all of our equations for things like temperature and wind and precipitation, then we can say something about it. This little cartoon here on the left just as an example of different types of physical processes that we actually try to solve and represent in these models. And these are things like clouds. These are things like when the precipitation falls and it hits a lake or the streams, how fast is that runoff and where does it go? Like sea ice and what's happening with the sea ice. All these interactions, ocean circulations, all these things are represented in what we call this Earth system model. And then we use these Earth system models to try to project what may happen in the future. And one important thing that we do is when we run these models, we actually run them for what's happening now so we can understand that they're correct for what's happening now. And then we can trust them for when we run them in the future. Okay, so that's like sort of just your climate model 101. This is why we use climate models. So for AR specifically, let's go back to our basics. So what do we care about? We care about the water piece, and we care about the wind piece. So let's just tackle the water piece first. So what's going to happen to the water in a climate change world? And so this picture here, you can see it's a map of the US, and there's a bunch of blues and reds. And the reds are just showing you where the most water, where it's wettest, where it's most humid. And the blues are showing you where it's not quite as humid. And so this sort of makes sense, right? If you go to Florida, or if you go someplace along the coast, it's humid, it's going to be wetter, it's going to feel wetter. So keep this in your head. This is what's sort of going on now. And then this image here is the same thing, but in a future climate where it's warmer. And so you can just sort of see by eye how the reds sort of pop out. And this is the difference between these two. So this tells us what's going to happen in the future relative to what's happening today. Is it going to be wetter? Is it going to be drier? And the answer is it's going to be much wetter. And so this is one piece of the equation. It's just generally going to be more humid, more water in the air, and a wetter environment in the future. So that's the first piece. So the second piece is winds. This is a little more complicated. So I've shown you here this little this picture here with the Earth and the different jet streams that are important for atmospheric rivers, just to sort of remind you what we're doing. and generally, when we think about what's going to happen with the jet streams, from like a general standpoint, the polar jets might move further poleward. So like the polar jet in the northern hemisphere will go closer to the Arctic, and in the southern hemisphere will go closer to the Antarctic. But there's a lot of wiggles and waves, and it depends a lot on what's happening in different regions around the world. The subtropical jet is actually a little bit more tricky. There's less understanding of what's going to happen with the subtropical jet. So going back to, remember, ARs follow remember going with the flow. ARs are going to track wherever the jet streams are. I'm showing you this image is just one example of a possibility where we're focused on the subtropical jet. And so where you see those oranges is where that subtropical jet could potentially be stronger. And if it is stronger, then regions like Southern California would probably experience more intense atmospheric rivers. This is one climate model that we're looking at here. And one of the things we like to do in the climate model world is we like to look at a lot of different models. And so there's different models may have a different realization of what this looks like. And so there is a lot of what we call uncertainty in this type of result, because we're really just, at this point, we're just really looking at one model. So we have to sort of take this with a grain of salt. Okay, so this is a little bit of a complicated figure, but I wanted to show it because it gives you a little bit of a bigger picture in different regions around the world. So I just really sort of want you to focus on the colors here. So again, we're going to look at both the water and the wind piece. So the water piece is this column, and the wind piece is this column. And here is our bar here, where it shows the deeper reds are stronger, and we're looking at, remember, the integrated vapor transport, which is this combination, and then the bluers is the weaker. And so we're looking at different regions around the world, West Pacific, Australia, South Pacific, South Africa. But remember from that first plot I showed you with just what's happening with the water, it's just going to be wetter everywhere. And this is also the case for atmospheric rivers. So this is specifically looking at atmospheric rivers. And so it's just going to be a wetter and more intense in terms of the water piece in these regions. Well, the wind piece is a little more complicated. We see blues and reds. So and it depends on where you're going. So there's a lot of, a lot of work still left to be done here. It keeps me in business to try to understand, what's going on with all these different regions and what's going to happen with the wind piece. So the bottom line here is it's just a little bit more uncertain. We really don't understand what's going on yet. Okay, so that was sort of like the water and the wind piece, but what about precipitation explicitly? So this, I hope these series of plots can illuminate that. We take a look at what we call our historical period, sort of what's happening now, represented by 1985 to 2015, and we're looking at precipitation as a form of these categories that we talked about. Category 1, which is sort of the mild category, and Category 5, which is the large category. And we're looking at the climatology here. So this is October, August through there on the horizontal axis. On the vertical axis, we're taking a look at the precipitation, but I don't really want you to care about the numbers. I just sort of want you to see the colors here. So here we have what is happening with the historical period. And this is what we project to happen in the future in years 2070 to 2100. And the grayed areas where this study is explicitly looking at and calculating these things. And so this plot right here shows you the difference between the two. So one of the takeaways here is that we do see more precipitation in these Category 5 types of storms. And this makes sense with everything that we've talked about, because as we know, as we go into the warmer world, that water piece is just going to get really intense. Okay, so now let's just step back and take a look at the globe in general, and I'm trying to sum all these things up. This figure summarizes a lot of the different scientific literature that's out there in terms of what we understand about atmospheric rivers in a future world. And there's a lot to look at here. So I'm just going to step you through a few things. So down here on this horizontal axis, this icon is frequency, and so that's this guy right here. The little geolocator is location. This means precipitation. This means precipitation extremes, this little hollow cloud with rain. And then the snow and the ice melt is this little teardrop-looking thing with the star in there. And then the house with the little wiggly lines means flooding. And this pink generally is just showing you areas where we have this general increase of moisture everywhere. So you can pick your region that you really care about and try to figure out, okay, well, what do we know? What do we know about it? And the red means things are going to get stronger, and the blue means things are going to get weaker. One of the things that I also want to point out here is that these grays, and you can see there's a lot of grays, means that we don't know yet, right? There's still more research to be done. And so there is a bunch of red here, but there's also probably more gray than anything else. So we still need to do a lot of work. I thought I would zoom in here with the US just so you can see this a little bit better. One of the things I wanted to pull out was even though we have red for all of these, for the frequency, for the extreme precipitation and the flooding, but one of the important things to understand about the frequency is that but we don't really understand what's going to happen with the location. Remember I talked about those jets, with the uncertainty with what the jets are going to do. What's going to happen with a subtropical jet, and what's going to happen with a polar jet. These are things that we're still trying to understand. And so we can't really say anything there. But we know that atmospheric rivers will go where the jets are. So if there's a location, say in Central California, that gets a lot of atmospheric rivers now, if that jet moves north, it won't get as many atmospheric rivers, but places north will. So you'll see an increase in atmospheric rivers to the north, but a decrease in that location. And so you sort of have to take these two things together. We know things are going to be more intense, but we don't really know where they're going to move. We have less of an understanding in that, especially for the Western North America. So this is sort of the takeaway. This is sort of the takeaway for this piece. Okay, so the other thing I thought might be fun to answer or just talk about is, does the shape of an AR change with warming? And in some ways, it sort of depends on what you're actually defining as the outline of the AR. There's lots of different ways where you can draw it. You can just draw this is the AR here, but this whole thing is the AR. So instead of worrying about that, let's just take a look at what's going on with atmospheric rivers as a whole. And so this image here is simulating a very strong atmospheric river as it occurred historically. This image here is showing you that same atmospheric river, but we're using greenhouse gases that will be in the future. So this essentially is simulating the same storm, but what it would look like in the future. And then we can see this core is much more intense, and it's a lot more blobby too. The edges of it are a lot more blobby. So the one thing blobby is a very scientific term, by the way. So the main thing to draw from this is that the core of the AR is essentially going to stay the same, but the impacts is what we really have to worry about. So the blobbiness. Okay, so the other thing I wanted to talk about was, is there a climate change fingerprint already? And so this is something that people ask me all the time. And so we're going to go back to this Oroville Dam storm as an example. And this, again, is another little bit of a complicated plot, but I'm going to hopefully step you through it. So the first thing we're going to look at is the horizontal axis that's stepping through time. And so we're taking a model run, and we're simulating this storm that happened at Oroville Dam. And the first thing we're doing is we're simulating it to make sure we get it right. And so that's the black line. And then the second thing we're going to do is we're going to take that storm, and then we're going to remove a bunch of greenhouse gases and pretend that this actually occurred back before industrialization. So we call that pre-industrial, right? And so definitely it's a cooler world. And so that's going to be the blue colors here. And then the next thing we're going to do is we're going to go to the near future, and then we're going to just add a little more greenhouse gases than we have now. And then the final thing would be to add a whole lot more greenhouse gases, and then so it'll be much warmer. And so this is that's the intensity, the IVT, the combination of water and wind, this is what it's going to look like as that progresses in time, from February 6th all the way to February 11th. And we can see that just by eye, you can see that what is happening now is generally more intense than what happened if it was just a pre-industrial type of a storm. So we do have a little bit of a fingerprint already. And here we're taking a look at precipitation too. And so each of these little bars represents a range of precipitation for each of these types of simulations. We don't actually see a fingerprint until we sort of hit the most intense parts of the storm. So like maybe from February 7th to February 9th. But we do see a significant increase in precipitation due to greenhouse gases that we can detect already. And then at the end of the storm, during the decay phase, it goes back to sort of the same. Okay, so the last few slides that we're going to talk about are about preparation. So I don't want to leave the impression of sort of like a gloom and doom that we're going to have these really, intense atmospheric rivers and there's going to be a lot of precipitation. Well, yes, that's true, but if we know that this is going to happen, we can absolutely prepare, and we can work with, the scientists and engineers. We can all work together to try to figure out, measure, like quantify how much more, how much more intense is it going to be, and what do we need to do to change and adapt to these new storms so that we can carry on as normal. And so that's what this project does. It was called Ark Storm, and Ark is sort of a play on Noah's Ark, like a lot of water in flood, so Noah's Ark. So the Ark HIST, which is this column over here, is showing you the historically the worst storm that we have observations for, and then we simulate it with a model. And then this right column is showing you that same storm, but we're adding a whole bunch of greenhouse gases, and we're going to simulate what it looks like, but in the future. And so we can have a guess of like, well, this is sort of like a worst case scenario that we could potentially prepare for. So you've seen these plots here. I showed you this example of our blobby shapes. And then up here are the images of what we call sea surface temperatures, and that's just the surface of the ocean, what the temperature is. And if it's warmer in a warmer world, which we can see with all of these reds, that those temperatures of the ocean that are warmer impact what's happening with the atmospheric river. So it's important to look at both of these things. Okay, so what are the types of variables that we actually look at that are coming out of these simulations? Well, that actually matter for everyone, for communities. Things like precipitation, but not just the precipitation, but the rate of precipitation. Like how fast is it really raining? In an hour, how much precipitation do we get? And then, where are we going to put all that water? And then the other thing we care about are things like stream flow and runoffs, like how fast are those streams going to go? And when are they going to overflow their banks? Or when is the dam going to break? And so we have these, things we can measure. Then you can work with city managers, engineers, et cetera, to try to, bulk up what we need to do in order to prepare. So these are things that are actively going on now. Okay, so I think that's the bulk of my talk. So I'm just going to summarize. The first point I wanted to make was atmospheric rivers are important for Earth's water cycle and local climates. The second point is that airs are comprised of water and wind. And hopefully you all totally know that now, because I've went over it lots of times. The third thing was water availability will increase in future climates, and we've seen this repeatedly, especially with the amount of water that we see not only in the globe, but in atmospheric rivers and the precipitation. And we'll likely actually have a little bit more intensive precipitation that we can prepare for. The fourth thing is changes in winds and jets and ARs will be regionally dependent. This is an area, it's active area of research, and there's still a lot of uncertainty in what's actually going to happen and where they're going to go. And that has to do with where the jets are going. And then by studying ARs in the future, we can prepare for any changes, so don't despair. And then I wanted to leave you with a bunch of little links I have for resources and tools. A lot of the stuff that I put up here is publicly available. That website for these really nifty plots is at a University of Wisconsin, and you can just go to that website and look at all these things to your delight. This earth.knowleschool.net is a super cool tool I use literally every day. I love looking at this thing. And then I got a lot of the drought stuff with the Colorado Climate Center at Colorado State. And then there's a bunch of operational centers that are really instrumental in providing observations, forecasts, and community building. Center for Western Weather and Water Extremes out of Scripps, the NOAA and the NASA group. And I also wanted to throw up here a group in Chile that is very similar to the CW3E, and they care about a lot about what's happening in South America. And so all around the world, people are caring about stuff. So, and that's all I have, so I guess we'll take questions. Thanks. So I wanted, the question was, can I address the difference between rain and snow for the precipitation for the ARs? And this is a very good question. How what precipitation does is going to matter on what the temperature is. So there are indications that the snow line will lower, or a high rate go higher, or the snow line will go and it'll rain higher. And so that, I think the more important thing is will we have enough snowpack, particularly for here in Colorado? Well, when we, as we move into the future, will the snowpack be sufficient? But the question of whether or not it's going to be rain or snow is really where you are in the world, and then what the temperature is going to be, if it's freezing or if it's above freezing. So, did that answer your question? Okay.
If you could raise your hand and wait for the microphone to get to you, we are live streaming this evening.
Yeah, hi. Can you hear me?
Yeah, I can hear you.
Okay, right here. Am I being heard?
Yes, I hear you.
So, two simple questions. Not really. That was a joke. So years ago, we used to hear about El Nino and the Nino cycles and whatever. I don't necessarily hear about that very much these days. And I was wondering if you can give me a nutshell summary of the atmospheric temperature conditions, and if you have salinity of the oceans in your model, or the dilution of salinity. So, very simple question.
Yeah, so I'll address the second one first. Yes, we absolutely factor in things like water fluxed into the ocean that will dilute the salinity, how salty the water is. And so that's absolutely in the Earth system models. So that, yes, that's addressed number one. The number two question, which was actually your number one question, was about the El Nino and La Nina. And so, El Nino and La Nina are a global phenomenon. It actually happens in the Pacific, but when El Nino produces an anomalously warm sea surface temperature, so that skin of the ocean is getting warmer, a particular region in the Pacific, that changes all of the weather patterns around the globe. And so how you change those weather patterns will influence where the ARs go. So, a rule of thumb could be with El Nino, you might get more atmospheric rivers on the western coast, but that's not always the case, because we've seen cases where, California was expecting a great water year because El Nino was happening, and then they didn't get anything. So there's still a lot of what we call variability between year to year, and even like one El Nino to the next El Nino, they're all very different. Yeah.
Hi. So along the lines of the salinity question, I think there was a recent article I saw in some magazine about the Gulf Stream current, and there's a different name for it, but that is, it was talking about the underwater waterfall that happens. Yes, the ocean conveyor basically in the Atlantic that's transferring a massive amount of water from the Caribbean up towards the northern, near Greenland, Iceland. And I guess I'm wondering if you can speak to those type of ocean currents and how those are impacting these atmospheric rivers as well.
Yeah, this is also a good question, how the ocean currents affect atmospheric rivers. So the ocean conveyor belt, I'm just going to sort of set that aside because there's these ocean circulations happen all over the globe, and that was you sort of outlined one piece to it. So rather than speak to like specific regions around the world, I'll just talk about in general what the ocean's influence on atmospheric rivers. And so I sort of alluded to it a little bit in that plot where we saw those sea surface temperatures. Let's see if I can go back here. This guy. We're looking at the skin of the ocean here, and when you have the warmer sea surface temperatures, that there is evidence that it produces it allows more water to go up into the atmospheric river and for it to become more intense. So it does affect the atmospheric rivers in that way. But I would say there's probably more of an impact of atmospheric rivers to the ocean than vice versa. So, for example, the precipitation that's happening, it will, this question of there about the salinity, it will get a little bit fresher with all that precipitation. But the most important thing is actually the winds associated with the atmospheric river will push the water around. And so when you have an atmospheric river bearing down on the west coast of the U.S., what's actually happening is you have a lot of water that's being pushed towards the coast. And so during the storm, it's actually like a little bit of a storm surge. And so then that would be impactful for communities. So.
Hi, thank you for coming. So if I understand what you're saying is the basic shape of it stays the same, but you were saying that the jet streams could change, and if they change, the ones that we're talking about could go north. And if the jet streams go north, then this kind of big, huge thing, river, would go north, which means that it would be hitting more like Washington and Canada instead of California. And I guess my question is that kind of what they're looking at? And if that happens, would the flooding and stuff be happening up high, up north, and then down in California, since they do have droughts anyway, if they didn't have the river coming by, would there be like even more serious droughts in California?
Yeah, I think you're understanding things fairly well. The only thing I'll amend was that the polar jet that could move to the north, and there is still, as I said, like a lot of uncertainty. Like when we talked about those models, not all the models agree on that, right? So that's why I say we maybe not really understand what's going on. So that's what's happening to the north. But remember, we have the subtropical jet. And that subtropical jet is also doing something. And some of the models actually have the subtropical jet actually getting stronger, which would mean more atmospheric rivers in Southern California. But, so that aside, if there is a dearth of atmospheric rivers, yes, drought will be will get worse, because atmospheric rivers really are one of the primary ways that California gets its precipitation. So without that, they will be in drought. But not only California, as I said, like the mountain snowpack will also decrease. And so communities that depend on the snowpack will also be impacted, not just California. Yeah.
Was the 2013 flood event here in the Front Range due to an atmospheric river?
I was waiting for this question, and I even have a slide. Okay. Okay, here we go. Was the Colorado flood an AR? Well, it depends on who you ask, because my personal opinion is that it was more of a monsoon. Right, so we had a cutoff low. So we had a low pressure system that was sitting over Colorado, and it was just sort of sitting there, and it was turning around. And then we had this monsoonal flow from the Gulf of Mexico that sort of got caught up in there. But there was also this piece. I think I got this as a a satellite picture. There's also a piece to it that, there was a moisture sort of coming in from the Baja in the southern, in the Pacific area west of Baja. So there are some people that consider that could have been part of an atmospheric river as well. So I would say, I think I have another slide here too. This one? Yeah, here we go. Cutoff flow meets monsoon. So, the far image over there is the satellite picture. You can see, the grays where it's wet. And then, but the main flow, you can see is in the middle, this middle panel here, it's really just sort of is coming in, which is more of a classic monsoonal flow. But that said, there are people, researchers and scientists that believe that all types of moisture transport, even monsoons, in some ways can be classified as an atmospheric river. So that's just like a semantic thing. I mean, this is more of a monsoon. I consider atmospheric rivers sort of attached to that low pressure system along with front is a different type of a system. But at the end of the day, it doesn't matter, right? It was an amazing amount of water, and it was a flood, and it was actually coming up either from the Gulf or from Baja. It doesn't matter. Yeah. So I don't know. It's a non-answer. So because I feel like there's a big argument in like whether or not some people say, yeah, it was absolutely NCAR, and other people's like, no, there was no low, it was monsoon. So it depends on who you talk to. So there you go. I'm not sure if that really answered your question. But I was prepared for the non-answer, so that's good.
Thanks for the nice talk. 2 questions. First of all, when you quantify the intensity of the atmospheric river and you assign a wind value, is that like a 500 millibar wind or a surface wind or is some sort of average?
So those winds, the integrated vapor transport, it's called integrated because it's integrated throughout the whole atmosphere. But the wind is integrated throughout the whole atmosphere. So that's like the surface up to like jet level, like 200 millibars. For those people, that's like really hot, don't know what the millibar thing is don't worry. It's just really sort of the top of the troposphere, close to the top of the troposphere, where the weather sort of happens. So that all that troposphere wind is being integrated. But it's also important to realize that all of the water lives in the lower part of the atmosphere. So even though you're integrating the wind, so that incorporates that push of the jet, the water piece is really the lower part of the atmosphere.
And then second question is, you showed some maps with drought conditions, for example, in California, and I've wondered this for a while. Is that a relative value to the normal amount of, let's say, soil moisture is for that region? So, for example, you could have much drier conditions in Eastern California than in Western, but not necessarily drought.
Yeah, and I don't know the answer to that. I don't know how they calculate that off the top of my head, but I'm pretty sure it would be like an anomaly, like the departure from normal. Yeah.
Thank you for the talk today. My question is similar to one that was earlier, that you mentioned that in a changing climate that the polar atmospheric river may move north and the subtropic may move some direction, possibly south. If they do separate, I think earlier in a slide you showed that moisture was actually coming from the subtropic atmospheric river and being picked up by the polar atmospheric river. So in a situation where those did spread or separate, is there concern that the polar region could have less water and the polar ice caps receive less snow?
The image that you're referring to is just sort of like a snapshot. And so we want to consider the climatology like over time. And so that was more of like those, the cartoon I showed with just the Earth with the polar jet and the subtropical jet. And the climatology is that we expect in general the polar jets to move poleward. What that means in terms of precipitation at the poles I don't think it necessarily means that there's not going to be precipitation there, because you'll still have storms that form. They're probably going to form a little bit further to the north when the polar jet is up there. But I think the more important question is how warm will it be, right? And how wavy it will be. And so how wavy these jets are is actually is still sort of an open question for research. So, how wavy it is, if there are going to be times where it's going to be really warm up there, and then, and then the next day it's really cold. So like, sort of like this, whiplash sort of a thing, hot, cold sort of a thing. So I think the concern for the polar areas is really more the temperature. I wouldn't be concerned about lack of storms. Does that answer your question?
Sure. I had one small other one. In the event in 3 weeks that our next president denies climate change is a thing that's happening, how concerned should we be that this type of research is funded and available to us?
Oh boy. I am hopeful that, well, first of all, the U.S. isn't the only one that's doing research, right? So I feel like science is generally well supported in terms of, it actually tends to be rather bipartisan science support. The climate question in general is something maybe not. But again, these opinions are all my own, by the way. Yeah, so I can't really answer that question, but I'm not really that concerned that the science will stop. The science will absolutely move forward. Yeah.
I wanted to get back to El Nino and La Nina. This last winter was El Nino. This winter is expected to be La Nina. And the jet stream definitely changes on the west coast there. So for El Nino, it's more to the south. So maybe Southern California would get some kind of straight across. But in El Nino, you have a whole lot more of the polar jet stream, and you get much fluctuation. So you could get lots of storms all over the northwest. So it depends on where you are. But it also seems the sea surface temperature is increasing or decreasing, and the swings between El Nino and La Nina are getting shorter and more extreme. So it seems like no matter what happens, you're going to get more violent weather. And how much atmospheric rivers and El Nino location of the jet have been studied.
So when looking at things like El Nino is definitely heavily studied, and we do have models that try to predict these. I think you're probably well aware of like El Nino and La Nina when they happen. Atmospheric rivers will, again, remember they track with the jets. So where the jets go, in response to El Nino, it'll be quite important. But it's also, I sort of mentioned this before, it's important to remember that, all El Ninos are not the same and all La Ninas are not the same. And so just because we have a La Nina coming up doesn't necessarily mean that we'll have the classic La Nina response. So there is still a lot of variability in what could potentially happen to like in a particular season. But from a sort of a climatology perspective, we just will go back to this idea that that as wherever the jets tend to track because of El Nino or La Nina, or because they're moving because of climate change, this is where the atmospheric rivers are actually going to go. It's just, it's not a satisfying answer because I can't tell you where.
Good evening. Thank you. I, for one, do not believe that we can control the weather. However, this does seem like, technology is out there, and this does seem like maybe there might be some way to control or interrupt or dam these ARs. And I'm wondering whether you know if there is research in this direction.
So what you're talking about is weather modification, and weather modification tends to be sort of a small scale sort of a thing, like, we want to throw some particulate in the atmosphere so, this ski area gets more snow. Attempts to change what's happening on a larger scale, so like hurricanes or atmospheric rivers, is not something that you can do. And I don't know of any research that is ongoing in terms of moving an atmospheric river. And I do know of research where we tried to impact the path of a tropical cycle. And this was like decades ago, I think in the 1970s. And that failed because that was just too small scale to be able to impact something as massive and powerful as nature's tropical cyclone.
We're going to take 2 more questions.
Okay.
I noticed that your models are very incremental. You add greenhouse gases and things get more intense. Do you push the models beyond that to where the whole system becomes more chaotic, and that your current view of the jet stream and other things break down?
So I'm not sure I understand what you mean by push the model to be more chaotic. Can you explain
Well, you don't push it to be more chaotic. You increase the parameters. Like if humans fail to control the greenhouse gases and you get beyond whatever incremental amounts you're adding.
Yeah, okay, I think I understand. So there is a lot of research out there that is actually not just increased greenhouse gases incrementally. I personally have done research where I've put a huge hit in there and increased it, 30 times what we have now, or 100 times what we have now. And I've also gone back into the deep past where I've, simulated, very cold periods and very warm periods. And so these models are very robust at simulating these types of wild, really cold Earth and really warm Earth. At some point the model will break down, but for what we need to estimate in terms of understanding climate change, models are well adapted and well prepared, or well built to do that.
Hi, back to Colorado. How many atmospheric rivers normally involve Colorado in a year? And is that very important for our water sources? And what's the future of Colorado ARs?
Yeah, so the Colorado ARs, the biggest source of impact for ARs for Colorado is probably the Colorado River Basin, and those are atmospherics that are sort of coming up from Southern California. And so those are the ones that we probably care most about. And so in the future, with a warmer world, we would expect a lot of that to rain out, and maybe not, there wouldn't be as much snowpack that would accumulate in the mountain ranges and the basins that we may need to supply our water. So that in that situation, we'll have less water to work with here in Colorado. Yeah. I think that's it. Thank you, everyone. Thanks for coming.